The James Webb Space Telescope is unveiling the universe in an unprecedented way, showing us truly shocking events. This telescope has been instrumental in revolutionizing our understanding of the cosmos, giving us the ability to explore the depths of the universe. Recently, it has made a truly astonishing discovery. It has detected 700 galaxies trapped in a black hole, including Stepan Quintet, a group of 5 interacting galaxies. We will delve deeper into this discovery and how it impacts both us and our conception of the universe. What we are seeing here is the chemical signature of water vapor. The James Webb Space Telescope is equipped with an array of advanced scientific instruments carefully designed to observe the universe at an unprecedented range of wavelengths. With a main mirror more than 6.5 meters in diameter, this telescope exceeds its predecessor, the Hubble Space Telescope. This allows the JWST to collect and focus light from distant celestial objects with unmatched precision and sensitivity. Instruments include a powerful near-infrared camera, a mid-infrared spectrograph, and a stepless spectrograph. These instruments work together to capture images, measure spectra, and study the properties of objects, ranging from the oldest galaxies to the planets of our solar system. One of the wonders we can find in the universe are black holes. These are cosmic entities that originate from the gravitational collapse of massive stars. When a star exhausts its nuclear fuel, it experiences a cataclysm known as a supernova. During this process, the outer layers of the star are ejected into space, leaving behind a dense core. If the mass of this core exceeds a certain critical threshold, approximately 3 times the mass of our Sun, the gravitational forces become so intense that they cause an even more pronounced collapse, resulting in a singularity at the center. A singularity is a point of infinite density and gravity, which cannot be observed directly. However, the James Webb Space Telescope has the ability to observe beyond what any other technology has yet achieved. One of the most surprising discoveries made by this telescope is the existence of 700 galaxies inside a black hole. This finding challenges the conventional understanding of how black holes work. A fundamental characteristic of a black hole is its event horizon, an invisible boundary beyond which escape becomes impossible, even for light. This boundary marks the point at which the gravitational pull of the black hole becomes so intense that not even photons, which are the fastest particles in the universe, can cross it. Any object or radiation that crosses the threshold is inexorably pulled toward the singularity at the heart of the black hole, a destination of no return. But most surprising of all, the extreme gravitational attraction near a black hole gives rise to a phenomenon known as time dilation. What happens in this situation is that as objects approach the event horizon of a black hole, time appears to pass more slowly compared to observers farther away from the black hole. This phenomenon, predicted by Einstein's theory of relativity, is due to the warping of space-time caused by the intense mass of the black hole. The event horizon is not a solid physical surface like the crust of a celestial object, but represents a mathematical boundary beyond which the structure of space and time behaves in a way that defies our intuition. The presence of an event horizon around black holes is what makes their direct study difficult. But this does not mean that it is completely impossible. Their influence on the surrounding space can be detected through effects such as gravitational lensing, which is a distortion of light caused by the immense gravity of the black hole. Gravitational lensing is a phenomenon predicted by Albert Einstein's theory of general relativity. When massive objects such as black holes warp the fabric of space-time around them, light from distant objects passing near these massive bodies experiences a bending in its path. This results in a visual distortion or magnification of the object's image. Massive bodies such as stars or black holes are especially effective in causing significant gravitational lensing due to their immense gravitational attraction. Black holes, in particular, represent one of the most extreme examples due to their incredible mass and compact size, leading to very pronounced lensing effects. When light from a background object, such as a star or a galaxy, approaches a black hole, it follows a curved path in space-time around the black hole, which causes the light to deviate from its original path. If the alignment is right, the deflected light rays can converge on a focal point, creating a discernible image of the background object. By the way, have you ever heard of white holes? The concept of a white hole arises from the mathematical solutions to Einstein's field equations in the theory of general relativity. These equations describe how gravity influences the fabric of space-time and predict a variety of exotic astrophysical objects, including black holes and white holes. While black holes are well supported by observational evidence and are known to exist in the universe, white holes remain purely theoretical. However, the mathematics behind general relativity suggests that they could exist as counterparts to black holes, representing regions in space-time where matter and energy emerge instead of being pulled inward. A white hole is fundamentally different from a black hole in terms of how it interacts with its surroundings. The defining characteristic of a white hole is that it only allows matter and energy to flow outward. Nothing can enter it from the outside. In contrast, black holes act as gravitational traps, pulling everything, including light, toward their singularities. This one-way nature of a white hole makes it an intriguing and mysterious object. While black holes are known to have an event horizon, a boundary beyond which nothing can escape, white holes have an event horizon that serves as a barrier preventing anything from entering. This makes them the reverse of black holes in a very literal sense. If black holes can be thought of as cosmic drains, where matter disappears, then white holes might be likened to cosmic fountains, where matter suddenly appears. Now, in theoretical discussions of white holes, intriguing questions have arisen about their temporal properties and their role in the universe. One of the most fascinating ideas is that time inside a white hole could be reversed relative to our normal experience of time. This means that, from an outside observer's perspective, processes occurring within a white hole might appear to be running backward. If this is true, it raises profound questions about the nature of causality, the sequence of events, and whether time truly flows in a single, unidirectional manner. Scientists have debated whether white holes could be relics from an earlier phase of the universe, possibly even linked to the Big Bang. Some theories suggest that the universe itself could have originated from a white hole-like event, where an enormous amount of energy and matter erupted from a singularity in a way that resembles the theoretical properties of a white hole. One of the most interesting aspects of white holes is their possible relationship to black holes. Some scientists have proposed the idea of a wormhole connecting a black hole and a white hole, suggesting that they could be different manifestations of a unified phenomenon. A wormhole is a hypothetical tunnel through space-time that could create a shortcut between distant regions of the universe, or perhaps even between different universes. If black holes and white holes are connected in such a manner, it could mean that anything falling into a black hole might not be lost forever, but instead could reappear from a white hole in another part of space-time. This idea is particularly intriguing because it suggests that black holes may not be endpoints where information is lost, but rather gateways leading to new cosmic regions. According to this idea, matter falling into a black hole could emerge from a white hole in a different region of space-time, or even in another universe. This possibility has led to speculation that white holes could be linked to parallel universes. If such connections exist, they might provide a mechanism for matter and energy to move between different realities, supporting some interpretations of the multiverse theory. This raises the possibility that the 700 galaxies detected in a black hole may have ended up there because of a white hole, and therefore, we are only seeing part of the story. Instead of being permanently trapped inside the black hole's event horizon, these galaxies might have entered a complex cosmic structure where they are in transit to another universe or distant region of our own universe. Furthermore, this idea relates to the concept of the multiverse, which postulates the existence of multiple universes, each with its own physical laws, constants, and conditions. The multiverse theory suggests that our universe is just one of many, coexisting in a vast and possibly infinite cosmic landscape. Some versions of this theory propose that black holes serve as bridges between these universes. If black holes and white holes are indeed linked, then it is conceivable that every black hole in our universe could be connected to a white hole in another universe, creating a vast cosmic network through which matter and information flow. This concept is not merely science fiction. It is grounded in serious theoretical physics. The study of black holes, white holes, and wormholes continues to push the boundaries of our understanding of space-time, gravity, and the fundamental nature of reality. If white holes exist, They could offer profound insights into the origins of the universe, the ultimate fate of matter that falls into black holes, and the potential for interuniversal travel. Future advancements in observational astronomy, such as next-generation space telescopes and gravitational wave detectors, may one day provide evidence supporting or refuting the existence of white holes. Until then, they remain one of the most intriguing and speculative ideas in modern physics, challenging our perception of the universe and the very nature of existence itself. These universes could coexist alongside our own, offering a wide variety of diverse realities. Within the framework of the multiverse, the hypothesis that black holes serve as cosmic gateways or connections between different regions of the multiverse, or even with other galaxies, is based on the extraordinary gravitational force exerted by black holes, which can significantly bend and warp space-time. What do you think? Let me know in the comments box. Remember to like and subscribe, and I'll see you in the next video.